Now it's time for the third keynote today, which is going to be slightly different because we've been talking about the author, we've been talking about the works. We had some examples from CREA, which is like a classical in the Rain Film Festival because they have been here in the first and the second year. The same for Runway that were here in our first edition just 2 years ago. But now we'll move to the audience to complement this first section of the research. And it's going to be this third keynote about the use of AI, not particularly generative AI, for analyzing, and the presenter will correct me if I'm wrong, yeah, for analyzing the audience, yeah, which is the one represented in our poster, in our image this year. The keynote speaker coming now is Gata Lapedriza. She's a professor at Universitat Oberta de Catalunya and a principal researcher scientist at Northeastern University. She will present emotion perception and representation in AI systems, and she will discuss current approaches and existing challenges to enable AI systems to perceive and interpret human emotions. Agata, thank you very much. Gracias.
Okay, thank you for the introduction. Can you hear me well? Test, test, yes? Okay, and thanks for inviting me. So nowadays we hear a lot about AI everywhere in the news and so on, but it's not that common to hear about AI and emotions. However, when we imagine the AI of the future, the robots of the future in science fiction books or science fiction movies, we usually envision these machines with some kind of simulated emotional skills or some kind of awareness about emotions. And the reason is that, and this here I'm illustrating different AI characters in movies, and these characters often express how challenging it is for them to deal with human emotions. And sometimes they even express that they would like to feel emotions or they claim to have emotions. But the thing is that if we imagine all of these machines of the future that are going to coexist with humans and are going to interact with humans, they will need some kind of emotional skills because emotions are so important in our social interactions. So to have this fluent communication with humans, we really need emotions. So it makes sense to imagine that the machines of the future that are going to be around us will have some kind of awareness of emotions. But this raises an important question, which is, how can machines perceive emotions? For instance, emotion perception is one emotional skill. And emotions are very challenging for humans, so sometimes we don't really understand how we feel. How can we imagine or how can we create machines that have these kind of abilities? So I'm doing research in emotions and AI, and basically all of the research that we do in trying to enhance the capacities of machines to perceive emotions and having other types of simulated emotional skills are based in three key ideas, which I'm going to illustrate here. So the first key idea is that when we experiment or express emotions, there are many signals in our body that change. So for instance, our physiology changes. So if we are stressed, it's very likely that our heart rate is going to increase. So this is going to be a change of physiological signals due to a change of emotional experimentation. We also communicate a lot with our faces and with, so smile, for instance, is a very powerful signal, social signal, and emotional signal, and so on. So we move our face depending on how we experiment or how do we want to communicate emotions. And for instance, our pupil dilates as well. So when we pay attention or are very engaged in something, sometimes the pupil changes. Our gestures, our voice, or the words that we say. So a lot of things that change when we experiment or express emotions. And the second key idea is that all of these signals can be captured by sensors. So for instance, I'm wearing a smartwatch that can capture my heart rate. But of course, we can use cameras to capture visual information, or we can also use microphones to capture audio and so on. And all of these signals are going to be represented in a numerical form, right? So images at the end large collections, like a big box of pixels, and each pixel has like 3 values, red, green, and blue. So all of these signals are going to be encoded in a numerical way. So which means that then we can use machine learning or AI, so this type of computational models, to process these signals and extract meaningful information about these signals. So to understand this a little bit more, let's focus on visual information and the cameras, which is the sensors that we use to capture the visual information, and the machine learning models that we can design to understand visual information from the perspective of emotions, as I was saying. And the reason why I'm talking about vision at the beginning is because my background is in computer vision. And when you think about visual information and emotions and understanding human emotions, the first thing that comes to your mind is facial movements. And the reality is that we communicate a lot with our facial movements. And there has been a lot of research in computer vision in detecting faces, detecting facial landmarks. This is a commercial system, what I'm showing here. And these systems are very, very robust nowadays. And these systems also analyze this configuration of the facial movement and map the configuration of the facial movement with prototypical expressions of emotions. Like, for example, here is illustrating happiness on the left, or prototypical expression of sadness on the right. So here, another example. So we run the same type of software, and we detect the face, facial key points, and this is going to be categorized as surprise because, the mouth is open, and this is a prototypical expression of surprise. But when we zoom out and we look at the whole image, we realize that, this kid is probably not surprised, this kid is excited. But what happens is that if we think about visual information and emotion perception, and we just rely on facial movements, it's not going to work, because some facial movements are not related to to emotion communication, are not related to experimentation of emotions. They are related to other things like blowing candles, which is an action. But there's another thing, which is it's very difficult to give an emotional meaning to an isolated face, because this is not natural. We don't see isolated faces in the world. We see faces in context. And in fact, there's been a lot of research from the psychology field on this, on how we perceive emotions from visual information. And psychologists were running this type of experiments. That's very cool. So they had like these facial movements, pictures of facial movements, and then they were asking participants, what do you think this person is expressing here or experiencing here? Is it anger, contempt, or disgust, fear? So, and they were realizing that humans were not agreeing on, what was this communicating. However, when they were providing more context, like here, so context is just an object, right? But in this case, with this extra information, people were agreeing that this was showing disgust. But if you change the context, and now it's just a gesture, people were perceiving this face as anger. So in this research, they were experimenting with this type of images with the same facial expression or movement, but contextualized differently. And they were realizing to what extent this context was influencing the perception process. And there are many, many works in psychology that show the relevance of context. And this inspired probably the first work in my lab that we did about emotion perception and how to enhance the capacity of AI systems to perceive emotions. And this is the project Emotions in Context. This started around 2015, so it's been a while. But still, some of the conclusions that we run from this project are very relevant and still drive some of the research that we do in my lab. So let's take a closer look at this project. So the idea was to approach this task, that just one single task related to emotional intelligence with this, which is this apparent emotional state recognition. And instead of faces, we want to look at the whole context. So we basically wanted to create computational models that were taking images as input and were creating as output emotion categories, like, for instance, confidence here. And for that, we wanted to train a deep learning model, which is a particular type of machine learning or AI system. Actually, all of the AI systems that you interact nowadays with, they have deep learning models in the back. So we wanted to train a deep learning model. But the first challenge that we face is that we needed data. So as you know, all of the AI systems are very data hungry, so they need to see a lot of data to actually work. And what we did at that moment is we created a data set because we didn't have any data that was representing the task that we wanted to approach. And we were collecting images from public data sets, and some of them downloaded from search engines. And then we were using Amazon Mechanical Turk for annotating the images. So basically, we were showing to annotators. We designed this kind of interfaces. There are more. This is just one example of the discrete categories, but annotators were seeing this image, and we were asking them, just check all the categories that you think this person is experiencing here or this person is expressing here. And then after that, we collected what we call the emotic data set. So we had 23K annotated images with 34K annotated people, because some images have multiple people annotated. And with this, we could train our deep learning model. And so just to give you some idea about the architecture of the model, so we have two streams. So basically, there's one part of the model that looks at the bounding box of the person and just extract information about the person, and the other one that looks at the context and extracts information about the context, and then you combine this information and make the final decision. And we train a lot of variants of this model with different types of loss functions and so on. I'm going to show you just one table of quantitative results. And we used, so when we want to evaluate if this works or not, we use evaluation metrics. In this case, it was average precision per category, which is an evaluation metric that goes from 0 to 100. 0 is terrible, 100 is very good. And here is the table, so I want you to pay attention into this column. So here you have like this measure for the different emotion categories, and the red column illustrates the performance of the best model that was just looking at the person, and the other gives the performance of the best model that we could train that used the person plus the context. So if you look at these numbers and you look at the average, you will realize that we get better accuracies combining body and image. So this is good because we could experimentally prove that the context was providing meaningful information, but still the average accuracies are very low. So chance would be 18, and here you have so chance would be 18 in average, and here the average is like 23, 27, and I said that this measure goes up to 100. So this really doesn't work. This is a very, very challenging problem. Emotions are very challenging. So in our papers, you can find qualitative results and more experiments, but some important conclusions and lessons learned from this work is that we showed this importance of the scene context for emotion perception in images, and since then we have been studying other types of context, for instance, cultural context. So emotions are, so depending on the culture, the same word of emotion, it's going to represent different things. So we have been studying to what extent this cultural diversity on how emotions are represented in the different cultures are aligned with the different AIs that we are developing nowadays. And another thing that is very interesting is that there's not, so emotions are there's a lot of diversity on how we experience and how we express emotions. There's not as much universality as we would like, which makes the problem very challenging. So it's not like training a system to detect expressions of happiness is not the same as training a system to detect if you see cars in the image, right? Because usually people agree of what is a car and whether there is a car or not in the image. But if something is expressing happiness or not, people are going to have different opinions here, and it's fine. We need to. So a lot of the research in trying to create these AI systems with emotions, with simulated emotion capacities, try to make the problem more objective. We think that we need to embrace the fact that it's not that objective, and we need to deal with this diversity and so on. So here, I'm just illustrating an example of 5 different annotators annotating the same image. So it's not completely the same, but there is some degree of agreement. It's not random. But still, everything that we saw in these annotations made us think we should think about better ways of modeling this diversity of opinions. And here I'm gonna present one set of experiments that we did to understand, to study these individual perceptions. We have more experiments, but this one focuses on one task that is relevant for this festival, which is emotions evoked by movies. So basically the task that we are approaching here, and notice that I'm talking about different types of tasks related with emotional skills, because what we want to study in general is how to enhance these emotional skills. So we work with different types of tasks. And here we were addressing this task of, imagine that we have an observer that is watching a movie. We want to understand what are the emotions that these movies are gonna produce to this observer. And for that, we use a public data set. It's called the Cognimus data set it represents 7 different movies, these ones that I'm showing here. And for each frame, there are 7 human observers, which are the annotators, and they are providing valence and arousal, which are the 2 most common emotional dimensions. So valence basically measures whether the emotion is positive or negative, right, in a scale from 0 to 1. Arousal is measuring whether the emotion is like calm and relaxed or whether there's a lot of agitation in the emotion, okay? And in this case, we focused just on valence, positive and negative, and binary valence, so not the continuous range of values from 0 to 1, but just we threshold this, and we had like positive versus negative to simplify the problem because we don't have that much data. Let's talk a little bit more about the data. So as I said, we have these samples, which are all of these clips of the different movies. And then we have 7 annotators in this case. So all these annotators are like watching the movies and providing all of these continuous annotations of how they are experimenting the movie. And then one thing that you can do when you have 7 annotators is to compute the average, right? So one says, I don't know, this is a 1, so very positive. The other says 0.8. The other says 0.2. So you can average and get a final score. And usually people work on modeling the task of predicting this average opinion of the observers. And they ignore the individual differences. But we wanted to embrace this individual differences thing, right? So what we did is we explored different ways of modeling this task where we really use all of this diversity of opinions in the modeling. Okay, so how does this work, this system, the eye system? So the eye system takes as input these video clips, right, which have different modalities. In this case, I'm illustrating, the visual modality, which is the video, but you can also have subtitles, right? So this is language, and there's information in the language as well. And there might be audio, actually. Here, I'm not illustrating the audio, but we were using the audio as well. So 3 different types of modalities. And that's important because each data modality needs to be processed differently from an AI perspective. And then the output is going to be this binary valence. So is this a positive, or is this evoking something positive, or is this evoking something negative? And here, the model uses also different streams, so 1 stream per each modality, so that you can process the data as the data requires. And here we have, the modality for the video, the modality for the text, and then we combine these features, and then we have the final decision. And we were experimenting with 2 types of architectures. So one of them is what is called the traditional single-task architecture. So basically, you're going to have your architecture, and at the end, you just predict this average opinion of the observer. But the other thing that you can do is you can have an architecture with multiple heads. So if you look at, here at the end, you have the prediction for annotator 1, the prediction for annotator 2, the prediction for the last annotator, and also the prediction of the average, which is the same that you are modeling here. And we are going to compare what happens when you do these 2 different approaches. So here I'm going to show the accuracy for the single task and for the multitask model for each annotator. So this is for the single task, and this is a binary task. So chance would be 50%. And here we have, 65%, so we are above chance, and on average, we are at 69 point, so almost 70. But when we use the multitask model, everything improves. So we are able to model each individual better than if we do it in a single task model, and we also improve on the average annotator, which is the task that is usually approached, and it's much better, and even the average of everything is better. So main observation of this work and all of the other experiments that we run with other types of data sets related with emotion tasks, we noticed that the multitask, so the idea of really embracing this diversity and modeling the diversity also to model the average experience was better. Another thing that we observed is that multimodal models perform better than single modality models. And what does this mean? So what I said is that in the movies you have multiple modalities. You have the visual, you have the text, and you have the audio, right? So the more information that you use, the better. And this happens in general. I'm going to illustrate other projects where this idea comes as well. But the idea is that the more modalities you have, the more context you have, the more information you have, the better you are going to do in these emotional-related tasks. And I guess that one conclusion is that our results motivate the interest of releasing individual annotations in future dataset collections. Okay, so now I'm going to move to another type of models. So far I've been talking about tailored AI systems that are able just to address one task. So in this case, this emotion perception in context with this specifically designed architecture for this task, or these other single task, multitask models, and so on. But nowadays, we have a different context. So from 2021, we start seeing the emergence of these large foundation models. So I'm sure that most of you have interacted with ChatGPT. So we have these huge models that are more general. They are not trained to do just one simple task. They are trained with a lot of data, a lot of data, but they have like general knowledge on different things, and they are very flexible. So they have never been explicitly trained to perceive emotions or to deal with emotions, but they have been trained with a lot of human data, like text descriptions or images. And all of these data are implicitly or explicitly representing emotions. So what is interesting is that even though they have not been trained to do any emotional task, there are some simulated emotional skills that are emerging due to the data that they have seen, okay? So it's very important that we understand these emotional representations in these models, because these emotional representations are going to influence they behave, are going to influence the way they behave. So I'm going to talk about one project where we have been experimenting with the OpenAI clip, which is one of the first models that appeared, and it's one of my favorite, actually. So just in case that you are not familiar with the details of clip, and you're going to learn a lot about models today, but I think that's my point. This is my research is in the technical approach, so I'm going to explain you how clip works. So clip is a foundation model that connects images and text, okay? And it's trained with a lot of pairs of images and text, like the one that I'm showing here. So here you have this image 1, which is an airplane, and you have a description of this image, which is an airplane taking off. Okay, another one, so this dog, and then the description, French bulldogs, best dogs for cities. Cool. Third one, this avocado image, and then avocado's recipe, whatever. Okay, so imagine millions of pairs of images and their descriptions. And now what we do is, as I said, both the images and the descriptions can have a numerical representation. And with this numerical representation, we can extract information and represent both the images and the text in a high-dimensional space. So this is the clip embedding space. So which means that each of these images and each of these texts are going to be projected in this 1024-dimensional space as a point. And all of this needs to be trained. So basically, this image encoder and this text encoder have a lot of parameters, and they are going to be trained with all of these images and text, following some kind of criteria, which is the loss function. And in this case, what we use is the contrastive loss, and the contrastive loss does the following. So it makes images and their corresponding text to be very close in this space. As points in this space, they have to be close to each other. And at the same time, they push away those images and text that are not corresponding to each other. So that's super interesting because it creates a semantic structure. So this is what we call the clip embedding space. And it has, let's zoom out a little bit and let's explore how it looks. So it has this semantic structure in the sense that it's going to have like the French bulldogs here and the avocados there and the airplanes all far away from each other. But there are going to be other images. So when you project other images and other texts related to these French bulldogs, they are going to be close to each other. If you project images and sentences about dogs, it's going to be close to the dogs because it learns this geometry with this semantic structure. And at the same time, close to the flights, you're going to have helicopters and other flying stuff. And then close to the avocados, you're going to have fruits and other types of vegetables. Okay? Why is this very powerful? Because then you can do a lot of things in this embedding space. And all of the foundation models and all of the tools that you might use nowadays in AI are based on this type of foundation models and embedding spaces. So one thing that you can do is zero-shot classification, which is very cool, meaning that imagine that you have this image and you want to do object categorization. This is a very typical task for computer vision. So one thing that you can do is you collect a large vocabulary of objects from a dictionary, thousands of objects or whatever, and then you create all of these prompts, a photo of a plane, a photo of a dog, a photo of a cat, a photo of a house, and so on. And then you project all of this in the clip embedding space, and you just check the distances, and you classify the image with the object that has, that has the sentence or the prompt that is closer to the image. Okay, this is the zero-shot classification with clip. So one natural question when we think about all of this rich space that can represent images and can represent text is this space representing emotion somehow? How can we know that? How can we characterize if something is represented here? Okay, so we have been working on exploring the emotional knowledge encoded in the clip embedding space and also in trying to use this clip embedding space for visual emotion perception, okay? And for that, we're going to use data sets again. In this case, we're using a WebEmo dataset and other datasets that have similar structures. So in this case, are large collections of images that are annotated with one emotion category. So again, you have humans that tell, this makes me feel happy, or this image, I see sadness, whatever. So you have one emotion category per each one of these images. And you have like 264K images. So these are really, really large data sets. And then we experimented with different technical approaches. So one technical approach is this zero-shot classification. Very simple. So we can take any input image. We can create all of these prompts, like a photo that seems to express happiness, a photo that seems to express sadness, a photo that seems to express surprise. And then we encode everything in this clip embedding space, and we just check the nearest neighbor. So we check the closest sentence, and then, okay, this is going to be classified as happiness according to the clip embedding space. But we can do other things. So for instance, another thing that we did is using also the representation of clips, so projecting the image into this feature vector, and then just putting on top of that some other computations, a few extra layers, and then doing a classification. And this is trained with a loss that is called cross-entropy loss, but basically it's going to compare probability distributions, and it's going to create a system that is able to classify the image into a collection of categories. Okay? So it's not going to be flexible to any open vocabulary, but it's going to be just, able of classifying into all of these categories. Another thing that we can do is using the same type of idea of having a lot of prompts. So we can, with the image category of the image, this is a different approach. We could use, so if this image is labeled with zest, we can create this prompt, a photo that seems to express zest, and then we can use automatic image captioning. In this case, it's going to produce a photo of a man jumping off a cliff at sunset. And then we can use synonyms on zest, like enthusiasm, energy, and so on, and create all of these prompts, and then just use the same strategy to learn another embedding space. This is not the clip embedding space, but this is exactly the same idea. I'm just transforming this with another type of text encoder and some transformations, and also train with this cosine similarity laws, but we are gonna deformate the original space in a space that is more suited to perform this type of emotional perception task. Okay, and then let's see what happens when we train and test on this data set with these approaches. So these are some baselines, okay? And here, this is the accuracy that you have when you try to classify in 2 categories, so just positive versus negative, 6 categories. So this is a hierarchical structure. So you have positive and negative, and then you have a few positive and a few negative categories with 6 categories, and then you have 25 categories, okay? So this is a hierarchical structure of categories. And this is the type of accuracies that you get with systems that have been explicitly designed to do this task, just this classification task on this data set. So what happened when you use the clip space? So this is clip without any training. This is just the skills that emerge in the clip space, okay? So we observe that the accuracy is really, really high. But it's really high in the 2 categories, but when you go to the finer grain, it's a much harder problem. It doesn't work that well. When we use the clippy cross entropy, however, this gives the best results. And when we use the contrastive, so the other architecture that is more flexible, we also get very good accuracies, which means that this is and this has the advantage that this model is very flexible. So training with minimal effort on top of these large embedding spaces, we are able to perform these tasks in a way that work really, really well in comparison with previous methods that were explicitly tailored for this type of tasks. And we have more experiments in our papers that show, that the systems based on this large and flexible embedding space are actually able to generalize much better. Okay, so now I'm going to jump. So I've been talking a little bit about the fundamental research that we do in my lab about how to create these AI systems that can deal with emotions. I'm going to talk a little bit about applied research. And in this case, we are focusing on a specific task, and we are trying to just address this task in a more controlled environment. So one of the things that we have been working in my lab in the past 5 years is emotion perception in the domain of assistive driving technologies. So this is just one example, okay, of applied research. And in this case, so there's a lot of interest in trying to create, so we hear a lot about autonomous driving, but the reality is that nowadays we have cars that help us drive more safely and more pleasantly, right? So imagine that the cars of the future have some kind of copilot that help you, just drive and notice when you need to pay attention to something and so on. So if you imagine this type of copilot, they should have some awareness about whether you are experiencing stress, whether you are experiencing fatigue, and so on. And the fact is that we experience extreme emotions while driving, and these emotions can affect our mental health and the road safety. And that's why in the automotive industry, there's a lot of interest in trying to make driving safer and more pleasant, and they are interested in this type of emotion perception of the driver. And here, going back to the beginning that I was talking about sensors and so on, so in this specific type of environment, you can be very creative about the type of sensors that you put in the car. So you can have cameras, you can process the audio, but for instance, you can put pressure sensors in the steering wheel, because when you are nervous or stressed, you're going to press more. So there's going to be meaningful information. And ideally, what you want is to, again, not just rely on a single signal, but to collect as many signals as you can and combine wisely these signals. So what we observed is that most of the research that was done in the past is based on putting sensors inside the car and extracting information of what's going on inside the car. But the reality is that we drive in a context, right? So that's my thing, context. And the idea is, if I tell you, just imagine yourself driving in scene A or scene B. So probably, and if I ask you which of the two you think are more stressful, so usually people agree that scene A is more stressful because there are more unpredictable things happening here, right? So you have cars, you have pedestrians, while in the other, there's nothing, right? So the hypothesis is that there are some objects and events that are visible in the driving scene that are informative to understand this subjective stress. And what we have been doing is trying to design these models that can analyze the context and provide this extra information about the context, okay? And we use this type of data. So basically we have drivers that are driving and they provide stress. So there's someone with them helping collect continuously this level of stress. And we also have physiology, so electrodermal activity, heart rate, and respiration rate. I'm not going to talk about this. But we have also a camera pointing outdoors, recording, the scene, the video of the context. And the task is taking the context, this video, and trying to predict the driver-provided stress, okay? So we are creating this type of models. In fact, so the best model that we have so far with the data set that we are working with, it obtains 72% accuracy in a 3-class problem. So we are simplifying, again, the problem in just 3 classes, like low stress, medium stress, and high stress. So these results are pretty promising and interesting. And so one thing that is interesting, too, in this research, and this is something that we apply to other areas as well, is that we use explainability. So explainability means that we are trying to understand what information in the input produces the stress, okay? So explainability is the area of research that tries to provide some more understanding on how the models encode the information and how the models produce the output. And that's very important. So in this case, we use this type of explainability technique, which we developed in 2016. But basically, this is a video that has been classified with high stress. And this is showing in red the areas of the video that are more associated with this high stress recognition. One thing that is very cool is that you can segment the image, so basically detect every object in the image, and then you can cross this information. You can check what objects are overlapping with these high stress regions, okay? And this allows you to suddenly learn about what are the visual patterns that are associated with the stress. So with this explainability technique, the system is able to automatically say, the presence of pedestrians and pedestrian areas, such as sidewalks or crosswalks, are highly associated with high levels of stress, while the presence of vegetation and non-obstructive views are highly correlated with low levels of driver stress. And this might seem very obvious, but the nice thing of this is that it's automatically discovered by the AI. Okay, so this is the type of output of the system. So basically, this is the video. Here you have the segmentation of the objects, and here you have, the areas that have, so the elements in the scene that are detected as high stress. So imagine your car integrating this and using this information in addition to all the other information to help you drive more safely and more comfortably. Of course, this has limitations. There are promising results, but this is a small data set, just 45-minute drive of 9 different participants, and all of the data was collected in Tunisia because we have one collaborator that is based in Tunisia. So, okay, so I'm gonna just, I guess that I'm gonna just mention another project, which is all of these. I have still 5 more minutes. Okay, so this assistive driving for adults and all of these technologies that we are developing inspired another project, which is assistive driving for kids, very different. So some of the research that we do in emotion perception and AI with emotions and so on is related to health projects. And in this case, the idea of this robotic car, so we designed this robotic car with the same type of sensors, and the idea is to reduce the stress of kids before surgery. So kids experience a lot of stress before surgery, as you can imagine. And in particular, there's one moment before entering to the surgery room where kids, where they need to go through these formal measurements of temperature and a lot of vitals, and that's a very stressful moment for them. So the idea that we had is if we can create this kind of robotic car where the kids can ride and they can go from the waiting room to the surgery room, and in the meantime, we can distract them and we can capture all of these vitals, we can avoid the most stressful moment right before entering into the surgery room. So the goal of this research is to reduce anxiety before the surgery, and the hypothesis that through distraction we can reduce the stress and take vitals at the same time. So this is still work in process, but so basically the conceptual design of the car started from in MIT when I was there a visiting researcher, and then we had a collaborator from Hyundai that helped us have funds in Hyundai, and in Hyundai they produced the car, so they created this prototype in South Korea, and it was shipped to Barcelona, and we are running the experiments in Sant Joan de Déu de Barcelona, so in the Children's Hospital in Barcelona. So if you are interested to know more about our pilot, so here you have the reference. So in summary, I think I'm fine, yeah. So what I know I gave a lot of information today. I hope it was not too overwhelming, but I wanted to provide technical details about the research that we do, because I think that it's gonna give you some information about the tools that you can use to create and how they represent the information and how we design these type of tools. Anyway, so in summary, remember that at the beginning I talked about these three key ideas about the signals and the sensors and the machine learning, which is, what supports all of the research that we do. And then I talked about fundamental research or challenges that we face when we want to create these machines that can have this type of social, emotional awareness or emotional simulated skills, like the importance of context. How can we incorporate context? What type of context is important? How do we represent the context? How do we use the context during the inference process? This idea of individual differences. So emotions are not objective. That's what it is. And I think that it's very important that we embrace this idea in order to create AI systems that have like a proper representation of what emotions are for humans. And then this idea of that these large AI systems that we nowadays interact with, despite they have not been explicitly trained to have emotional skills or awareness, they have them because they see data from humans, and data from humans have all of this information. And then I talked about these use cases. I talked about the assistive driving technology and the kids' car, but we also work with social robotics. So in general, we have different projects where we try to enhance the capacity of social robots to perceive emotional and social signals and to respond to these signals appropriately so that we can have more fluent interactions with machines. But of course, there's a lot of interest about emotions in the entertainment industry, for example, in video games. So, for example, you can imagine that if characters of the video games are empowered by some kind of AI system, if they can properly encode emotions somehow, they are going to be able of providing a more engaging and more immersive experience to the user. And why not the film industry? So, in fact, emotions are so important in any creative process, right? So if we think about developing AI to support or to assist in creative processes, it will be useful that this AI somehow can represent and have some understanding about emotions. And I'm going to conclude here. I don't know if you have any question.
Gail. Thank you, Agata. A lot of questions. Yeah, 1, 2, 3. We have 7 minutes for questions, and we'll finish this first slot. Thank you. Kyle, there first. Okay.
Hola, ¿puedo hacer la pregunta en castellano?
Sí.
Sí. Yo quería saber, porque en esto de las emociones solo tenemos las herramientas de la imagen. Yo, por ejemplo, tengo la duda, por ejemplo, en un psiquiatra, un enfermo que tiene una depresión, te cuenta y tú lo ves, pero el paciente puede estar fingiendo. ¿Cómo podría una inteligencia artificial saber que lo que parece es? Gracias.
Okay, well, ¿contesto en castellano o English? Okay, so yeah, that's a very interesting question, and it's very complex. So some of the research that we do, in fact, we are partnering with clinical psychologists right now, and we are running some research around how to create AI systems that can help better monitoring, for instance, patients that have been diagnosed with depression. We have, okay, so there are, I guess, two things that are important regarding to your question. First is that in an emotion perception scenario, we have different ground truths. And actually, let me see, because I think I have a slide for this. Okay, so this is the emotion perception scenario. So imagine that you have the target person, in this case, the patient that you said, right? And you are interested in understanding the emotions that this patient is experiencing. And this is one type, which is the experienced emotion of this patient. But the thing is that, as you said, sometimes you experience one emotion, but you don't want to share this emotion with others. So you can intentionally express another type of emotion. And this is happening during the communication process. And then there's an observer who is going to perceive an emotion, which can be different as well from the experience, the expressed, and the perceived. Because this observer is going to be conditioned by their internal state, right? Their personality. So there are a lot of things that also filter your attention and your understanding of the emotion. So as you said, it's very complex. Depending on the use case, for instance, in the research that we do for reducing the stress of kids before surgery, we are really interested in the experienced emotion. So things that you can do is collecting as much information as possible. So for instance, adding physiological signals is important, because physiological signals are going to provide extra information on top of the visual, on top of the words, on top of the audio. So that's one thing that you can do. But okay, there are other ways of approaching this. So for instance, one thing that we are doing right now is using wearable sensors to collect information about behavior. So if we think about depression, there's a strong correlation between depression and reduction of movement. And it's not clear what is the cause and what is the consequence. Is that you reduce the movement and that's why you get depressed, or you get depressed and there's an effect, this affects your metabolism, and then you'll move less. So it's not clear what's the cause and what's the consequence, but there's a correlation. So one thing that you can do is extracting information from the patient between one doctor appointment and the following one, so that you can get more objective information about how this person behaved and moved during the weeks that the physician didn't see the patient, and then use AI to extract more objective information for the physician to make better decisions and better assessments on the progress of the patient. That's another thing that you can do. But in the case of, I don't think, so we are not thinking about designing AIs that are analyzing an interaction between the physician and the patient, because maybe it's not necessary. But providing extra information to the physician when the physician is not seeing the patient, this is something that you have a gap, and here AI can help. And I said a lot of things, and I don't know if I answered everything, your question exactly. Okay.
Thank you. I have two questions.
Okay.
First one, you mentioned in one of the studies that you used the Amazon Mechanical Turk platform to do the research.
Yeah.
And there's very worrisome research about the work conditions of these people, the hourly wages, the time that they have to respect to do these annotations. And I was wondering if this was an issue of concern in any way,
Yeah.
and also if you try to understand where they are located, because on the platform they appear with the kind of coded numbers, but they may be in Kenya, in the US, in Mexico,
Yeah.
and that of course the culturally located position may also influence, and the working conditions, their annotations. This is the first question. The second one has to do with the fact of relying on the clip embeddings. Do we know where these text image pairs came from that were used to do these embeddings? Because if clip, like in other cases, use the alt texts for the embeddings, that is also a very questionable way of describing images. And I wonder if this is also, as far as I know, OpenAI does not disclose
No.
as Lion 5B instead has done the sources of. But I know that in Lion 5B, for example, the text-image pairs are mostly alt texts. Can this be a reliable source for describing images and especially describing emotions in images?
Okay, so I'm going to start with the last question. We don't know what are the pairs that have been used for training CLIP, of course. I mean, OpenAI does not release that. But as you said, there are some other systems that have similar architectures, and they release the data so you can explore, the influence of the data. The fact that the texts are old, I guess this can affect the representation power of the embedding space. But here, what we are doing in this research is trying to characterize the representation of emotions in this embedding space. We are not questioning to what extent this representation is optimal or not, depending on the data that has been used for training them. Then, regarding the first question, yes, that's an important point. So in our case, this data set was annotated in 2016, so it's been a long time, and things have changed a lot. I don't think I would use right now Amazon Mechanical Turk. At that moment, it was very, very common in the computer vision community. So what we did is we restricted the annotations to the US, and one of the reasons is I talked about this cultural difference about emotions, and we wanted to make sure that we had some kind of consistency, and we decided, to be restricted to Western culture and in particular to the US. And then about the hourly rate, so the workers can decide whether they want to engage in a task or not. So what we did is when we created the annotation task, we did the task ourselves to quantify the amount of time that was required. And then what we computed, I think it was like $10, $15 per hour. And then, so at that moment it was pretty good pay, I must say. So we had a lot of annotators providing feedback, and they were having fun with the task. And they were going through some kind of training first to make sure that they were understanding the task, and then they were annotating as many batches as they wanted.
Thank you. I think I'm going to continue with Antonio's question, because he, when talking about the Mechanical Turk, he was talking about the cultural differences and how's that taken in consideration. And my extension of this question is like, okay, we need to have some way of considering that honking and when driving in some cultures is just like a way of communicating. The other one's like really aggressive. And so how does your laboratory research takes these differences into consideration? And also on the output, because if you think of industry, like the ultimate goal is to have one model that can be released and works everywhere, and that's a real problem. And it's a big problem also for us in generative media, because we end up with this so-called slop, which is pasteurized, homogeneous images, text, sounds, which take no consideration for individual cultural differences. So how does you face these issues?
Yeah, so for instance, as I said, for the emotions in context, we just annotated in the US, and then for the driving experiments right now, we just have data from Tunisia. So we usually start from, studying in a specific geographical location. The reason why we decide, the reason why we decide one geographical location and not another is usually for convenience. In this case, we had a collaborator in Tunisia, and they were taking care about the data collection. So of course, whatever works in Tunisia might not scale to everywhere. So that's what I'm saying, that there are limitations in this work. So it's not ready to scale up and be used anywhere. Ideally, anything that deals with emotion, you need to run user studies in different geographical locations and make sure that you adapt the technology to the needs of or whatever cultural context you have in the different geographical locations. And there's a lot to be done to actually have machines that can deal with emotions in the wild, anywhere in the world, and so on. So there's a lot of work to be done. We're just making tiny steps.
I have a comment, but I can talk later.
Okay.
Okay, thank you very much for the questions, and thank you again, Agata, for your wonderful presentation.